Jumper offsets are used to go around cylindrical objects and return to a similar parallel path on the other side of the object. The diagonals are usually at 45-degree angles. There are two different common patterns. The one on the left uses two 45-degree elbows and one 90-degree elbow, whereas the one on the right uses four 45-degree elbows. The other variable that will need to be considered is the elevation of the horizontal pipes in relation to the center line of the obstruction. Notice the diagram on the right, the offset piping leaves at a higher elevation. So pipe D will be shorter than pipe B. If it had have entered or left lower than the center line, then the diagonal piece would have to be longer. If we were to try and cover all of the options in this video, it would be a very long video. So we'll focus on identifying the secondary triangles that you will use to solve these types of questions. I must warn you, at this point you should already be familiar with the math that we've been using to solve for parallel offset questions. So I won't be explaining the math as much as helping you with the triangle visualization. Remember, you can always pause and rewind if you feel like I've gone too fast. So let's start with an example of the pattern on the left. The information that you will usually be given is the diameter of the cylindrical obstruction, the clearance from the outside of the object to the center line of the pipe. Also, the distance of the horizontal piping from the center of the obstruction. You will notice that we'll always use the center line of the cylinder as our reference point for the visual secondary triangles. You'll first calculate one of the diagonal pieces by drawing a secondary triangle out from the center of the object at 45 degrees from the horizontal. This will create two right-angled triangles. The short side of this triangle will be the radius plus the clearance. Then it should be pretty easy for you to see that the length of the diagonal run to the horizontal center line reference point will be the short side times 2. If pipe A was aligned with the horizontal center line, then we'd be done with our calculations for the length of pipe B. But as you can see, that's not the case. We need to calculate this extra length right here. We're given the distance y below the center line, so we could draw a small triangle and use y times 1.414 to get the extra length that would be added to our center line diagonal calculation. Now that we have the total length of B, we can use that to calculate pipe A. Let's draw another triangle that includes length B as the hypotenuse. You can see that the short side of this triangle, deducted from dimension E, would give us our length for A. We can easily calculate the short side by dividing our length B by 1.414. Now, the procedure for the other side is pretty much the same. The diagonal to the center line would still be the radius plus the clearance times 2. On this side, though, the length C will be shorter by the amount that we can calculate using Z times 1.414. And now that we have dimension C, we can draw our triangle that gets used to calculate D by subtracting C divided by 1.414 from dimension F. Okay, that was a lot, I'm sure. So take a breath, and we're going to look at the 445-degree elbow pattern next. Here we go. Just like the previous example, the first step is to find your secondary triangle that uses the radius of the obstruction and the clearance to the pipe. So the length of this side will be the radius plus the clearance. But that only gives us part of diagonal B. Now we're going to draw out from the center of the obstruction to the center of this elbow. You may remember doing something similar to this when we discussed parallel equal spread offsets, where we concluded that this angle only made half of the change of direction. These three lines now form a 22.5 degree right angle triangle, where we're given the side adjacent and we're trying to find this short side opposite. Do you remember the tangent of 22.5? Yes, it's 0.414. So, to solve for this side opposite, we multiply 0.414 times this adjacent side, and we get this short dimension here. We can use that to add to our previously calculated length of the secondary square to get the total length of B. For dimension A, we can use the secondary square short dimension to calculate its hypotenuse, which gets us here. So deduct this from F, and you get dimension A. Okay, let's take a look at C now. When we drew our line out to the center of the elbow, we created a duplicate triangle right here. Now I will say it's duplicate as the assumption is that the clearance from the tank is to be maintained at all of these locations. So let's draw some more of these lines on the other side. You can see we have 4 identical triangles, so the length of C is 2 times our previously calculated opposite side of this 22.5 degree triangle. Now let's look at pipe D. Notice it doesn't line up with the center line of our obstruction. If it did, then length D would be the same as our previously calculated length B, which remember we got by using the radius plus the clearance to create the short side of the secondary triangle plus the opposite length of this 22.5 degree triangle. But notice where it takes us to. Dimension Y, which will need to be given to you. So I'm going to create another 45 degree triangle that uses Y as a side. Now we can use Y times 1.414 to calculate the hypotenuse of this little triangle. Then we deduct this dimension from this length here to get D. And lastly, let's get length E. Remember, we calculated the hypotenuse of the secondary square previously when we were solving for A by multiplying the short side of the secondary triangle times 1.414. In this case though, we need to deduct the length of Y to get us to this point. Then we could subtract this length from G to get the length of E. I realize that was a lot. My assumption is that you've read through the examples in your textbook prior to this video. If not, go through those now, and you may want to watch this video again.